Okay, may as well get started here. So this is kind of a follow-on to the talk 2 years ago. That was the Issaquah challenge and was one approach to dealing with it, and we'll be looking at a little bit beyond the Issaquah challenge on this one. I asked a little bit earlier, but I'll ask again so more people can. How many people were at the talk in 2014? Okay, so several of you, that's good. Well, this talk relies a little bit on that. We'll do a little bit of a review to catch up, but if you're here, you have a little advantage. Those are the topics we're going to cover. First off, I'm going to do is just kind of review what the Issaquah challenge itself was to give a starting point and then show what we're doing beyond that point. So the point of the Issaquah challenge is you have binary search trees, and you need to be able to move stuff from one tree to the other atomically. And that means that if a reader goes and looks in the right-hand tree and doesn't see element 4, that if it looks in the left-hand tree, it better see it. Okay, so it has to be atomic in that sense. And also, the other big thing, and then the same thing for element 1 in the other direction, the other big thing is that in this case, there's no relationship between these guys in a data structure sense. They're entirely different parts of the tree. And so it's a requirement that these moves be carried out with no contention whatsoever. Okay? And that means no lock contention, no memory contention, no nothing. All right? And that means that most solutions based on locking, in fact, most solutions based on a lot of things, just need not apply because they will have contention, lock contention, or if you use some of the non-blocking synchronization, you'll find yourself doing cases on the same element. That's contention, sorry, out of the pool. Okay, so the next slide is just kind of a quick history of where we've been with this. The very first thing after the meeting Issaquah in February 2014 was a C++ paper. The presentation here, I followed up at LCA with better scalability, which we'll see. At conference in June, I made some changes. The main thing was laziness on my part. I was getting ready to start implementing some of this stuff for real and realized that meant I had to have 2 copies of every algorithm. You'd have a hash function for just RCU lookup hashes, and then another one for if you want to do atomic moves. And that deeply offended my inner sense of laziness. And so that meant I did more work to avoid that, so we can just use one underlying algorithm and wrap other stuff on top. Of course, that means we start from ground zero on scalability and reliability. And I've made some of that up, but I haven't made it all up. Anyway, here we are in September 2016, looking at another round of this. I'm just going to quickly run through this. Some people would argue that parallel updates are a solved problem. We got hash tables, we have locks in each bucket, and randomness should work. You should have no contention. Life should be wonderful. But if you actually try running it, well, your global blocking, you'd expect that to be horrible, and it is. But per bucket locking, that's the wonderful stuff for the updates, and it falls off there. And this is a log-log scale, so that drop it looks gentle, but it's not. All right? And we'll see that, and we'll see that on the next slide. Yeah, poof, down hard. We can get some of that back by making the hash table bigger. Okay, we don't have that many CPUs. We only go up to 60, but still with 124, you've got some chance of them running into each other. But we never really, it's still a cliff. It's a shorter cliff, but it's still a cliff. And the problem we have is a little thing called the laws of physics. The thing is that the machines we have are set up kind of like this. In fact, in the talk just down in the theater before us, there was discussion about NUMA and the effects it had, and we're having that here. We split our computers up into pieces. It takes time to get the information from one piece to another, and that shows up in our performance results. The speed of light isn't all that fast at this scale, and the speed of electrons or holes, depending on how we look at it, is even slower. We are not a vacuum, we're silicon, essentially, and we're not light, we're little particles. Not only that, it gets worse. We are not just transmitting a signal from one point to the other. We're going through a bunch of clocked logic, going through caches, going through cache coherence protocols, going through bus protocols. Things get slow. But if we could get rid of all of that, we still have 2 fundamental laws of physics that are actually constraining enough to be a problem. The first is the speed of light. Sorry, it's finite. Now, there's been some variance in the measurement over the past century or so that people are measuring it accurately, but it's still finite. The other problem we have, and this is not mine, Stephen Hawking made these observations at a tour of a lab some years back, is that atoms are not zero size. The problem we have is that a transistor is kind of cartoonishly structured kind of like this. You have a base in the middle, and the electrical width of the base controls how quickly you can switch the transistor. And about 10 years ago, we had bases that were about this many atoms thick, like 4 or 5. Okay, they had scanning electron microscopes of these things, pictures of these things. I don't know where they're at now, but I know they've made these in research labs and actually operated them. I don't know what the production transistors look like, but we're probably not far off of that. Now, there's a bunch of things they could do in hardware, and they will do in hardware. Vacuum tubes, believe it or not, are making a comeback, and might be making a comeback in silicon. Rather than have that base be atoms, have it be a gap, right? It turns out at these scales, the atmosphere is essentially a vacuum. The odds of a molecule of air actually hitting that junction at that point in time is vanishingly small. Your radiation is a higher probability in some sense because you don't have to actually hit directly with the radiation. But still, we have some serious limits we're up against, and we don't know how to abstract these away. I mean, some people say they do, but I always look at what they do and their performance results aren't consistent with it really abstracting it away. But abstraction may fail us, but dirty tricks and workarounds are still with us, and we can make those happen, all right? I've been doing this for a long time, and well, you know, one trick, which I have used a lot over the past 20 plus years, is read mostly access. You see, if it's read mostly, you don't have to communicate it. You can just get it out there to start with, the Akamai trick, except applied inside a computer, and before Akamai was thought of. You just make sure the data is spread out everywhere it needs. It's read-only, it stays in the caches, and you get instant access to it. Life is wonderful. Unfortunately, sooner or later, if you want your computation doing the interesting, you're going to have to update something. I mean, you might be able to prove me wrong on that, but every time I've come across something, sooner or later, you have to update something. And you know, we got these little values replicated out, those little black squares, that same value replicated out everywhere. As soon as you update that value, sorry, poof, all gone. It's now back where in the updater's cache, and everybody else has lost it. The update operation was expensive, although the CPU designers usually overlap that with everything, so you don't notice it as much. Write buffers, wonderful things. But the next time those other guys read, they get the full electrical price across the system to get that value back, and that hurts. Well, there's tricks and workarounds for this as well. One of them is to leverage locality. This is a big thing with sharding they talk about across distributed systems. We do the same sorts of things inside of systems. For example, replicating statistical counters across all the CPUs or all the threads. You increment your own counter. You want to read the thing out. You sum them all up. And if you're incrementing a lot and summing seldom, like you might if you have an operating system that receives packets, increments a counter for each packet received, and maybe every 5 seconds or a minute or so, it puts out the sum to some kind of monitoring system, works great. So there are some workarounds. And I guess one way to dodge it is don't write unless you have to, at least a shared memory. If you're writing to your own memory, okay, that's not so bad. And if you can do a read-only traversal and then only write at the edges where nobody else will notice as much, that can be helpful too. And we'll talk about that more. And if you can, you want to shard the data and give each CPU its own little piece and not have them talk back and forth, although sooner or later they usually have to. The problem with hash tables, of course, is you have a hash function. And that means your accesses are sort of random, although you can cheat and use a hash function that chops the CPUs up, and it's been done before. Trees are really nice for this because they spread things out. Unfortunately, there's this bit about having to rebalance them every once in a while, and that is difficult. Although it's easier with skiplists than with other things, apparently. Although, again, skiplists don't need it as much because they kind of are random. But life's like that sometimes. Okay, I'm going to go through this next part pretty quickly because it's just what you'd expect. If you lock at each node and keep going down, that's a really bad idea because everybody locks the root. That becomes a bottleneck. Everything is slow. The contention all over the place. Don't do it, okay? I'm going to go through this part pretty quickly too. We're going to have a talk. Magid Michael Wong, and I will be presenting on hazard pointers in RCU and concurrency toolkit, so there'll be a little more information on this. Plus, there's references into the slide set and other things available. But the idea behind RCU is that you just let the traversing things read. You don't require them to do updates to note their presence. And then the updaters have to be careful in order to avoid disrupting the readers. All right? And yeah, a little care is required. And I'll just quickly go through insertion. What this is 4 different states, 3 transitions between them. We have a very simple linked data structure, which is just 1 pointer and 1 element hanging off of it, maybe. To start off with, we don't have any element hanging off of it, null pointer or null and C, which is where I'm at usually. We allocate a new data structure. It has garbage in it. Okay, no problem. Nobody can get at it, so it's okay that it has garbage. The only person that has access to it is the guy that's allocated, assuming your memory allocator is working, which I hope it is. Then the next thing we do is initialize it. Still no big deal, nobody else can see it. And then we assign it into the pointer. The reason we use a special thing instead of an equal sign is that the compiler and the CPU can often mess things up for you. But once we do that, suddenly everybody can see it. But because we stored it carefully, that pointer store is a single instruction, a single store. That means somebody racing who reads from it, if you're using proper C atomics instead of just assignments. And even if you are using assignments, the compiler's going to have to be a little bit, well, I don't know, malicious to get at you, but some might. What happens is that anybody loading that pointer will see either the null value, the old value, or they'll see the new value, but they won't see some mush of the 2 values. And that means that no matter what they do, they either see a null pointer and see nothing there, which is fine, or they see your structure properly filled out, which is also fine. Okay? So what this means is we can insert things into a linked structure without having to do anything to the updaters. The updaters can just go around and do stuff to us, and the readers don't have to exclude them. They can run in concurrently with them, and it works out fine for insertion. And there are it's kind of surprising. There are actually a fair amount of software that uses just this and does stop the world tricks when they need to get rid of things. Okay? But stop the world can be a little annoying, so we'd like to remove stuff as well. Same situation. This time we're going to get a little more complicated. We're going to have a 3-element linked list and remove the cat. Now, if we store the pointer from the boa to the cat and we make it point to the GNU, and we do that again using C++ atomics or something equivalent, so that we just store the pointer in one shot, that means readers see either the pointer from the boa to the cat, or they see the pointer from the boa to the GNU. They don't see some mush of the 2 pointers. Now, they may disagree as to whether the cat's there or not at a given point in time, depending on when they show up and when they get preempted and all that stuff. But they'll all see a valid list. And if we could somehow magically wait for all the readers to get done, once they were done, no new reader can find the cat, only the old readers can be there. So once we wait for all the readers, there can't be anybody but the updater with a reference to the cat. And at that point, we can free the element, overwrite it, do whatever we want to it. The readers can't see it. Okay? Of course, you do actually have to implement the synchronized RCU magic operation. And the readers aren't leaving any, in the most aggressive case, if you compile a Linux kernel for a server with config preempt equals n, you will get this case where the readers leave no trace of their presence in memory. Okay? But we still have to deal with them, and we do. We cheat, as always. What we do is rely on the fact that in non-preemptive environments, if you're holding a non-preemptible resource, a spin lock, for example, you're not allowed to block. If you did block while holding a pure spin lock, you would deadlock. You've got the spin lock, you block. Everybody else tries to go for the spin lock, they spin. Well, they're not going to stop spinning until they get the lock. You're not going to get a CPU until they get the lock. Until you get the CPU, you can't let go of the lock, and life is hard at that point. So we use the same rule for the readers. Okay? If you're reading, you're not allowed to block. What that means is if you see a CPU block, that means that all the previous readers have to have finished if everybody's following the rules. On the other hand, if people fail to follow rules, no synchronization mechanism in the world will help you, right? You can break anything if you're malicious about it. Well, that means that once we see all three of these guys context switch, so we remove the cat over here, we desynchronize RCU, meant we blocked, so we're done. And as soon as this guy does his context switch, that reader's done. And finally, this guy, the third guy and last guy, does his context switch, he's done. Now, the only reader that could possibly see the cat's this guy, but that's okay. It's okay to be a little longer than need be. We're just returning memory. Once we've seen all three of them, that means no reader can possibly be seeing the cat anymore, and we can free it, or override it, or do whatever. Okay, and what that means is that the main thing is in the middle there. RCU is synchronization via social engineering. The primitives, in the most aggressive case, opt in the developer, who has to refrain from blocking. If he does RC read lock, he has to not block until he gets to the RC read unlock. Just like all the other synchronization mechanisms, if you are going to use transactional memory, you'd better have all the relevant accesses in a transaction. If you don't, it won't work, okay? Similar with locking, and there's avoid data races is a big thing in the C++ memory model. The thing that's unusual about RCU isn't that it relies on social engineering, but that in some implementations it relies solely on social engineering. And the nice thing about that is that there's not a whole lot faster than doing nothing. Doing nothing is pretty fast, it's pretty scalable, it's energy efficient, there's a whole bunch of nice things about it, and in that aggressive case, we can do with that. We can take advantage of that. But there's a downside. That downside is that it is specialized. The best place is things like networking stacks, where there's, or any kind of a situation where you have a data structure in the computer that is tracking some external object. Because of our friends the speed of light delays and the atomic nature of matter, that data structure is out of date. If something changes, it takes time for it to be updated. Therefore, any algorithm dealing with that has to deal with the fact that there will be times when it is stale. In those situations, this works wonderfully because the fact that you might see something old, well, you might see something old anyway because the update might not have got to you yet. Something may have changed out there, but you haven't seen it yet. Therefore, if some of the system has seen it and some of it hasn't, that's still okay. In the case of routing tables for TCP, you may send the packet the wrong way, but you've probably been sending the packets the wrong way for quite some time because the routing update hasn't gotten to you yet. And if you send the packet the wrong way for another millisecond or so, nobody cares. Okay, but that's not all algorithms are that way. There's some of them where you need consistent data. So for example, in Linux kernel, RCU is used to mediate the translation from a System 5 semaphore ID to the internal in-kernel data structure. Well, it's a foul. It's really bad to let somebody do something to a semaphore that got deleted a moment ago, okay? You can't allow that. And so we have to apply some additional synchronization. We have a lock on the in-kernel data structure itself. You mark it, say I'm deleted. You release the lock. There it comes in. He finds it because he got there a little fast. He says, oh, I've been deleted. Okay, I pretend I didn't find it. And that works pretty well there. If you have a lot of updates and you need consistent data, there are places, for example, where this is used in the Linux kernel. For example, the translation from path name to inode structure is an example of that. However, if you update mostly you need consistent data, you probably should be using something else, okay? There are a couple special cases we come across where it actually does work well, but usually if you're down there updating a lot and using consistent data a lot, you should use something else. So, of course, that means that's a challenge, and we try to do it anyway, which is where this presentation is at. Okay, so what we do for read-only traversal to update location is we use RCU to keep the stuff nailed down. So we're in a read-side vertical section. That means that if we get a reference, and by reference I just mean we get a pointer to it. We haven't done anything with smart pointers or anything like that. No reference counts, no anything. We just have a pointer to it. That thing cannot disappear. It cannot be deallocated until we exit the read-side critical section. That means we can just traverse down a tree. We enter the read-side critical section, we traverse down the tree, and once we get to where we want to go, maybe where we're inserting, or the thing we looked up, or the thing we deleted, then and only then we acquire locks. All right. Now we may have to do some checks, and we'll talk about that a little bit. We may try to delete something that somebody else just deleted. We have to detect that and retry, much as you would for something like sequence locking in this case. Okay, but if we get there and the checks pass, then we release the locks, we go, and we're done. There's quite a bit more on this. The idea has been around for a long time, maybe back to 1980. It's not a particularly new idea. Using it in an organized way and actually using it in production is somewhat more new. But well, my kids are all out of college now. When Jack and I started doing this, they weren't in kindergarten yet, so it's been around for a while as well in our use. Okay, I'm going to go quickly through the solution of the Issaquah problem, and we start off with the tree here. And the big thing here is that because RCU is specialized, what that means is we use other synchronization primitives in combination with it. We don't try to go it alone. And so we have different domains in the data structure that are doing different things. So we have RCU protecting the upper part where we're traversing it. And that's really important because if we actually did something on those top nodes, we'd end up with a really horrible contention. And we have to avoid that. Even if it wasn't a rule for the Issaquah solution, we still want to avoid it because it's expensive. So when we get to the bottom, though, at that point we need the consistency, so we rely on locking. Now, locking is only going to protect a point update, and we need something that deals with this atomic move from one tree to another, and we're not going to have a lock spanning both trees, at least not if we want to scale or perform well either. So we're going to use existence structures to mediate that, and we'll show that in a moment. I'm not going to go through this in detail. These are just the 4 cases you run into when you go down without locking and try to update something and it's broken. One of the things might have been deleted or something might have been stuck between them. And you could use some very complicated recovery mechanisms. What I currently do is just start the thing over. Okay, and then as just drop the locks and retry. You could, if you retry too many times, actually acquire locks all the way down. There's a bunch of stuff you could do. I haven't had to do that yet. So what's an existence structure? Well, we're adding another level of indirection. This is the common computer science approach to the world. And initially, in fact, in 2014, I was actually adding 3 levels of indirection just to keep things going. And the trick here, and I'm going to just show I'm just going to step through this without explaining it. But the idea is that you can flip one value, this is yellow existence switch, and change the existence or not of a structure. Now you could have any number of structures tying into this thing, and what this allows you to do is kind of synchronized on-off switch on any number of structures that are making up another structure. All right? We'll go through an example showing that in a real tree in a moment. But 3 levels of indirection was too much for Dmitry Vyukov, and he says, come on, McKenney, get your act together. Do it this way. This, of course, takes us outside of the C++ standard. You're not allowed to tag pointers, but it's really convenient. A lot of people do it, so I'm doing it too. The idea is that the existence switch is big enough to be aligned. That gives you some bits on the bottom. So instead of having this extra 3 levels of thing, you just use the bottom bits of the pointer and they either match this integer or they don't. If they match the integer, this other thing out there exists. Otherwise, it doesn't. Okay? So it's a fairly simple computation. If the pointer is null, then it exists because it's not changing at all. And we'll represent this structure like that with just a little rectangle with the red and blue parts of it, just because otherwise the diagram would get too full when we showed the example in the tree. But the same thing applies. What happens is that by doing a store into that existence switch, okay, it starts out 0, which means A exists and B doesn't. We store a 1 into it, and bang, suddenly A doesn't exist and B does exist at the same time. So with a single store, we can make any number of data structures pop into and out of existence at our control. Okay? So let's apply this to the 2014 problem, which is our tree, and this is our initial state. We want to, as one atomic thing, move 4 over to the left-hand tree and move 1 over to the right-hand tree. So we want, no matter what a reader does going through here, it can't see anything that would show those being non-atomic. In other words, for example, it can't see 1 in this tree, and then see one in the right-hand tree, and then see 1 in the left-hand tree. It can't see 4 in the left-hand tree and then go around and see 1 in that same left-hand tree, because that would mean it was a non-atomic update. It can't see anything that indicates that both of them were one tree at the same time, or that there was a time when there was nobody there. So the first thing we do is we get an existence structure. We allocate a new 4 and a new 1. And you can use indirection if you want to make a common data structure, or you can do copying. Pick your poison. And we start off with element 1 existing and element 4 existing, the dark green ones. And the thing is that we had to make a change here. But the change didn't really change anything. It just made the computation more expensive. So before we added this, element 1 in the left-hand tree existed. And you could tell because there's a null pointer there. After this, element 1 still exists, and the way you tell is there's a pointer, and it goes off, you check the bits, and they match. That says a 0 on the bottom bit, this thing has a 0 on the bottom bit, life is good. And elements 4 and 1 that are coming in, there's no big deal, nobody can see them. So we can make this transformation non-atomically and not affect the readers, aside from making their computation a bit more expensive, making their life more difficult, I guess. Okay, the next thing we do is we actually add the new 4 and 1 to the tree. We can again do this non-atomically. Beforehand, they didn't exist because you couldn't find them. Afterwards, they don't exist because you look at the bottom bit of their pointer, it's a 1 and it's a 0 still. The blue part is the one that's the current state, all right? So beforehand, you went and that brown node and you saw a null pointer, nobody's there. Afterwards, you go, oh, there's a 4 here, but no, its pointer, bottom bit of its pointer doesn't match, therefore it doesn't exist, pretend it wasn't there. So we can make this change again as slow as we want. We are just inconveniencing the readers, making them a little slower. We aren't changing their answer. The next thing we do does change things. We store a 1 into that existence structure. When we do that, suddenly the existence of the 4s and 1s exchange. So the old 4 and the 1 that used to exist don't anymore suddenly, and the new 4 and 1 that didn't exist now suddenly do. And the readers coming in, because that's a single location, if they see it in one state and then they see it in the new state, by all the memory models we have and by the fact that you do a relaxed load, you have to get coherence. If you do a relaxed load of a variable and then later on do a relaxed load of that same variable, you're required to see them in order. And therefore, we get this atomicity. Unfortunately, it isn't quite that simple. You have to do acquire a load of the pointer itself. But life's hard sometimes. Once we've done this, people really don't see that 1 on the left or the 4 on the right. I mean, they go through some work to see they don't see it, but it's not there. And so we can non-atomically remove them from the list. And once we've done that, we can clean up. So that's the basic sort of a thing we're doing. And this is, you may recognize this is kind of one of the components that some transactional memory implementations use. It's in some ways kind of similar. So we have existence pointers. If it's null, it's there. Otherwise, you check the bit and the thing it points to, and you better have a good API. I'm not going to go through the API in detail. It's here if you want to look at it. But if I didn't have an API, I know I would have a really hard time having something equal null being it existed, all right? So you have to put it behind something. So this is kind of an overview of what it looks like. You've got some kind of data structure header, you've got an existence head, you've got a user pointer. If you need to have stable pointers to the things while they're moving around. Obviously, you could take this green thing and have 2 copies of it, once in each structure, if the long-lived reference to it while it's moving around to different data structures is not required, and if it's small. Okay, so that's kind of what it looks like. This is pseudocode for the move, and basically goes through what we're going to do there. This is the old stuff, so I'm not going to go through this in detail, and it doesn't like me right now. Well, that was exciting. Let's try this again. Okay. If I can remember where I put it, this would be much easier. There we go. There we go, okay. And it says if I want to recover it, yeah, I'd kind of like to, thank you. Let's try this again. Okay, well, that looks promising. Let's see if it'll put up with me going through this quickly. Got to stress test it a little bit. Let's see if it does it this time too, you know? Okay, we're so far so good, so far so good. I do have a PDF, you see, if worst comes to worst. Okay, all right. And I'm not going to go through that in detail. What I'm going to do is go through the performance results we had. Last year, we got to 80 on 60 CPUs, and we got to, in LCA, we got to about 90. And you may wonder why you're getting 90 on 60. It's because of the cache effects. This is super linear scale up, beat up because the more CPUs you have, the smaller piece of the structure they're looking at, and the less cache they use. Okay, that was read-only. If you add a small amount of updates, things get a little bit worse. Only 40x on 60 CPUs. This at least beats Bjarne's 10x he wanted this morning, I heard. And if you're only doing updates, this is on 8 CPUs. Things were really horrible back in June of 2014. They were a little better at CppCon, not much better at LCA. However, one nice thing about the LCA results is that if you add more CPUs, you still got better up to about 32 CPUs. What happens with 32 CPUs is that this is an Intel machine that has hyperthreading, and it's one of the older ones that has thread 0 through 31, and then thread 2 on the same cores from 32 to 63. And this thing's able to use more than half of a core. So you get a nice slope, and then you don't get quite as much out of the rest of the cores. Still room for improvement, but that's not, it still beats Bjarne's 10x. You know, not bad, maybe kind of okay, not great, but all right. But as I said at the beginning, this requires me to modify my algorithms. It's not a big modification. You just have these little thingies, and you go through your tree thing, you traverse it, and you say, does this thing exist in a few places? And then you have to have a way of backing back out to start over if it doesn't. But still, it's different, and I didn't want to maintain 2 different ones because I was lazy, which meant I did much more work to avoid the laziness. So the goal is to be able to take just an RCU tree lookup algorithm or just an RCU hash table algorithm unchanged. All it knows how to do is insert, delete, lookup. That's it. It doesn't know anything about this atomic stuff. And make it so that it can support atomic moves among a bunch of different data structures. In fact, we want to make it so if you have a skip list and a hash table, you can atomically move stuff from the skip list to the hash table and back, all right? Why mess around, you know? I guess you could argue the whole thing's messing around, but okay, fine. Gotta have some fun, right? So this is kind of what we're doing here. So we're going to start off with rotating elements through hash tables. So we're going to take, first off, we have element 1 in hash table 1, element 2 in hash table 2, element 3 in hash table 2, and we're going to kind of rotate them. So when we get done, element 2 is going to be hash table 1, element 3 is going to be hash table 2, and element 1 is going to be hash table 3. And we're doing that atomically. It's going to happen all at once as far as the readers are concerned. A reader going through, there's nothing it could do to ever see a time when there were elements, when each hash table didn't have one of the elements or other, or any time when a hash table clearly had both of them, all right? So no matter what it does, there's only 3 elements, and each hash table at any given time only has one of them. Okay, what we start off with is we're going to make these existence things. And we mark some as incoming and outgoing. And these are hooked up to these. I ran out of space. I'm sorry, I don't have the little diamonds. But you can think of each one of these things have a little diamond hanging off of it and pointing to the right thing of it. And we have the existence structure down here. It says 0. That means the things that are outgoing, which have a 0 on the bottom of their pointer, exist now. The incoming ones, which are tagged with 1 at the bottom of their pointer, don't. That's why they're red. So if you look up in hash table 1, you'll find element 1. You won't find element 3 because it's marked as not being there with that red incoming guy. However, as soon as we store a 1 to that yellow existence structure, everything changes all at once. And we have atomically rotated those elements through those 3 hash tables. And then once we've done that, we can just clean things up, and we end up with something looking like that. And what happens is that on the incoming things, we store null into the pointer. And if it's a null pointer, it doesn't point to any existence structure at all, that means it unconditionally exists. So these things become white permanent things. The outgoing things, we pull them out and free them up because Nobody's looking at them anyway, and life is good. We've rotated. The data is fairly similar. The trick we do here is that we put an element, this HEHTA thing, this HTLM, that is a hash table element, all right? And all the RCU hash table thing knows is that thing. It doesn't know or care about the rest of this stuff. And so we just hand this to a normal hash table algorithm, and it hashes it and throws it in the right place. We can tell it to remove it. Everything's fine. And on top of that, we layer code that uses the rest of these guys. For example, this existence head structure, which is going to point to one of these existence flip guys. We use those to implement the atomic moves on top of the structure that is just an unchanged normal RCU algorithm. And then once we do that, this looks a little bit ugly because I wrote it, therefore it looks like C, okay? Sorry. You know, it's encrypted to you guys, you can convert to C++, and I wouldn't understand it either. But still, it's pretty straightforward. What we're doing is we're allocating the existence thing, that's a big yellow thing. The top allocation is a big yellow thing at the bottom of the Proust diagram. We make sure we got one, we initialize it so it's there, we do an RC read lock. We allocate the new existence structures for the place we're going to, and then we set the ones that are going away to outgoing. We don't need RCU anymore. We do existence flip, which essentially just does that store, and we do call RCU to free them all up. The existence flip, all this stuff maintains lists of the things that are coming or going, and so existence flip flips the value and then cleans things up, either freeing up the stuff that's going away or storing zeros into the appropriate place of the stuff that's staying. So it does the tracking for you, a little bit of it anyway. So that's all you need to do a three-way rotation through hash tables. You allocate the thing, you go through and you make the new existence structures, you set the old ones to being outgoing, you flip the switch, and the outgoing ones no longer exist suddenly, and the incoming ones are there. And then that frees up also frees up the extra stuff. And then we call RCU to get rid of the existence structure itself. And this is kind of a cheat because I very carefully reverse engineered the hash function to make sure I had absolutely no contention, and therefore the outgoings can't fail. All right, they're always there. Normally you'd have to have a check there and do an exception or something to get out if you conflicted with somebody else, if you didn't have some other way of organizing it. And again, the big thing about this is you can have an RCU protected hash function that knows nothing about atomic move, and on top of it you get atomic moves. And the next question is, well, how well does this perform and scale? Well, for readers it's great, but as I mentioned at the beginning, I kind of had to start over on both reliability and scalability from ground zero as of a few months ago. And so it's not so good, would be a polite way to put it. On the other hand, this is down here. I'm using RCU in a problem where I've said many times it's stupid to use RCU, okay? But you know, sometimes you gotta do something stupid. And the other thing is nice about this is an opportunity to improve the infrastructure. If you abuse something and it breaks, you fix it, you may make it work better for things that aren't abusing it. So it's not necessarily a bad thing to do. My usual traditional quote, providing perfect scalability and performance is like committing the perfect crime. There are 50 things that might go wrong, and if you're a genius, you might be able to foresee and forestall 25 of them. As you can see, that list is not 25 long, so there's some work left to go. Well, I did over the last week or so get some more stuff, and so a little bit more filled out. One of the problems I'm having is that this thing just kills memory allocators. I mean, these things just were not meant to handle a producer-consumer relationship where you're just jamming elements down one side and just allocating them out the other. None of the allocators handle that well at all. I cheated and made a special purpose allocator that's just a lockless queue. The thing is that I know the thread that is freeing things up, I know the thread's allocating, and I just pass the stuff back. Stupid, but it works. So that helped a little bit, and that made it so I actually got positive scalability, although you'll notice that I'm not getting nowhere near the order of magnitude that Bjarne would like to see. Okay. Again, I had to start over from ground zero. I am doing better than I was last June, so I've gotten a little bit of improvement out of it. But I mean, we're at 2 on this side, and we got 7 CPUs. You want to be 14 over here, not at 6.5. Okay. I mean, pretty straightforward. Plus, I'm only using 7 threads, so you really want to be using at least a few tens to even show you're serious these days. Okay, well, that's hash tables. What about skiplists, right? Well, this is the same diagram we had before, except it says SL down up on the top. I mean, it's exactly the same situation. And we do exactly the same thing, and they rotate around, and life's wonderful. And here, instead of having a hash table, we have a skip list structure and a skip list pointer to the head. And the code looks rather similar. You do pretty much the same thing, which probably means there's an opportunity for abstraction here somewhere. Although I'm beginning to conclude that premature abstraction is the root of all evil. But maybe that's just me. Anyway, and again, this skip list is just an RC protected skip list. It knows nothing of atomic moves or anything like that. It's just there. And this wrappers all that stuff on top of it. Unfortunately, it's scalability really is horrible. And what's happening here is with the hash table, I very carefully avoid any contention. And the skip list, I could make it avoid the contention, but I just let it randomly choose stuff. And so we do have contention, and therefore we have the line there. Skip list is kind of like a randomly generated tree. And what I'm doing is I'm having different threads deal with different subtrees. And the way the skip list is laid out, they will share some locks, unless you are very careful how you set up your skip list, which I wasn't in this case. Okay? All right, well, there's a bunch of things you could do to make that better. I could tune the skip lists. I could, I'm doing huge amounts of memory allocation. I could batch that up in various ways. There's a bunch of stuff I could do. But first off, let's just try, one thing you try is doing more elements, right? I'm taking 3 elements and rotating them through. And I'm paying a certain price just for the fact I'm rotating. So why not rotate more elements? And so you can do that. What you do instead of just rotating 3 elements, rotate 3 pairs of elements. Okay, so you rotate 3 triplet. I can't make a diagram of that and have it look at all reasonable, so I'm not going to try. But it's just, the thing is, instead of atomically moving 3 elements around and around through these hash table and skip lists, we have pairs of elements that were triples of pairs of elements are rotating around and around, or more of them, just making a bigger problem essentially. And this can be done. I did it, but and you'd expect the performance graph. You'd expect to go up and then kind of level off, right? As you do more and more of them, you amortize away the overheads of just doing the atomic move. And eventually you get to where just the memory allocation is hurting you. And that's sort of what happens, but it looks like that. I haven't had a chance to look at this. My guess is that I'm getting an extra cache line every 4th element or something like that. It's possible I'm also popping out of a page every 4th element. It does allocate more memory than it should, in some sense. And so, and if you count, you see 1, 2, 3 up, 4 down, 1, 2, 3 up, 4 down. It just does that all the way across. Nevertheless, we are getting better efficiency out of it. It is going up. Although we're coming short on this is on 7 threads, and we're still not quite making 25 million operations per second, 25 million rotation sets per second. In other words, I rotate 2, I count twice, right? And that's a little disappointing. But if you think about it, an even bigger mystery than those jaggies on the performance is, why would you do it this way? I mean, if I do 3 rotations, I end up in the same place I started. So why bother allocating and deallocating the memory? Okay. I mean, why bother? We're going to allocate, we're going to free, and we're going to go through grace periods on every one of these things. Why? Because we're just coming back where we started. Why not instead? The thing is a state variable. I mean, it's just a variable. And we got, on a 64-bit machine, you got 3 bits on the bottom of the pointer. All right? So you're not limited to there or not. You could have states. All right? And we could have 3 states, in fact. Except that, and then what I call this is a kaleidoscopic data structure. It's kind of like you turn the kaleidoscope, you get a different picture, right? Okay? And that's the effect you have. You just have these things, each pointer is tagged with which state it is. And then you can have the variable takes on one of those numbers, and you just match up or you don't, and you change the number and you get a different set of things coming or going. You can go further, of course. You can have multiple existence things working at the same time and update them separately, or you could use shifts and masks and have a 64-bit number, and then each pointer has a tag with it saying where in that thing it pulls its value from. Or you can even have you could do a bunch of things. I mean, you could go crazy. I decided not to. I just use the bottom bits and match them exactly with the integer, because that's all I needed. Now, I'm only showing 2. What I'm doing is I'm rotating from a skip list to a hash table. So I mean, I could have 2 of each, but it didn't seem fair to have 2 of one and 1 of the other, so I just have 1 of each. And what we're going to do is we're going to make that element 1 and 2 swap into the hash table, into the skip list, atomically. Same rules as before. Before we do the switch, if you look up, if somebody doing a lookup exactly when you switch sees element 2 in the hash table, it better not see element 1 in the skip list. Or excuse me, it better see element 1 in the skip list. I'm getting that back. Let me try that again. That was, yeah, okay, let's try this again. Okay, so if it looks up in the hash table and sees element 2 there, that means that the switch has already happened. Therefore, if it looks up in the skip list, it better see element 1. Okay? If it sees any evidence that the switch has happened, anything it looks at after that had better see that switch as having happened. And the way we can do that, we have our kaleidoscope structure. It just has a number. In this case, we only need 2 elements, but that's fine. And we have a state 0 thing, which used to be outgoing. We have a state 1 thing, which used to be incoming. And we could have a state 2 and a 3 and a 4 and a 5 and a 6 and a 7. We could do more than that if we wanted to go back to having 3 levels of indirection, but why bother? Now, it's initially 0, which means state 0 is the thing that exists, and state 1 doesn't. So currently we don't have element 1 in the skip list because that's state 1, which doesn't exist because the current state is 0. But we store a 1 in there, and suddenly they flip places, and now the hash table contains element 2, and the skip list contains element 1. And we could flip it again, and we could flip it again, and go back and forth. Now, and the loop to do this is kind of straightforward, right? You essentially just, while you're supposed to keep running the benchmark, you set your state to the current number of rotations %2, and you increment the number of rotations. And you can do %3 or %4 if you had more of them, whichever it was. And you'd hope you'd get pretty good scalability to that because all you're doing is doing a store release over and over again. And thankfully we do. In this case, we're doing linear scalability up to 32 and then tails off after that because we're getting more than half of a core just with 1 thread. But we're getting a factor of 32, which nicely exceeds Yarna's demand for a factor of 10. So, on the other hand, this is great. This is the kind of scalability I like to see. But we're talking about something pretty specific. I mean, you have to know what you want the data structure to do through time, and you're just changing it through a couple of set states. So, big lesson out of this is be wary of benchmarks, because this is a legitimate solution to that problem. It's just very fast and very restricted. Nevertheless, it's something that could potentially be useful in some situation, and it's possible that it may be something where we can use this with some other things to make some nice stuff happen. Advantages, disadvantages. This is not something you just wave a wand. You do have to make some change to your program. You have to, put some things in the data structures. I'm sure if I knew C++, I would just do a template, and suddenly bang, it'd be there, or inherit from this or that, the other thing. And I've started doing that a little bit with the RCU stuff, and it's been interesting education. And maybe I'll get to there here, or maybe somebody else will beat me to it, which is fine. Right now, this works for linked structures and not much of anything else. There might be some way of making it work without link, but one straightforward thing is to take your stuff that isn't linked and put it on the other side of a link, which of course gets you an extra level of indirection and an extra cache miss, and further down the road that CS always takes, the computer science always takes. You have to have explicit memory management. You could use this as a garbage collected language, I expect, but right now we're talking about memory managed things. If you wanted to take the same key and flip it back and forth, same key with different value, you would have to have a structure that could tolerate duplicate keys. All right? Mine don't right now, but you could do that if you wanted. We can have irrevocable operations. Well, you can do whatever you want while you're doing this stuff, and it's fine. You want to do some I/O, great. You want to do some networking operations, okay, whatever. You can exploit locking hierarchies to make it so that you can coordinate your updates if you have overlapping atomic updates. I haven't messed with that yet, but it's something that it should not be a difficult thing. The fact that we can get semi-decent performance scalability, we get great performance scalability if we benchmark the problem to death, but what else is new? And there's a lot more automation, and the fact we can use the RCU algorithm changed makes things a little bit easier. And this thing is a really mean memory allocated RCU test case, I'll tell you. I mean, you can find all sorts of bugs and all sorts of performance problems and scalability problems and those things really well with this stuff. When would you use this? I've had a couple people say they thought they might have something, but I haven't heard of anybody actually using this for real, all right? This started as a challenge. It wasn't intended to be anything real. It's just a, Paul, can you do this? Okay, sure. And it got kind of interesting, and I kind of got carried away with it. What can I say, you know? This is my best guess as to where it might be usable, or might be something you do. You know, many small updates to a big complex thing. I could imagine my best guess something with graphs maybe, but I haven't got to that point yet. Besides, if you haven't done it yet, you can always say it has to be that. It should be read mostly. You have fairly complex updates. There's a lot of overhead there. My bit about doing only updates with it is probably an abuse, but if you don't abuse, you want to abuse it before your users abuse it. I mean, they're going to eventually. If you abuse it first, you have a chance to fix some of your own bugs. It's kind of a good self-defense technique. The other thing is, if you need compatibility with old hardware, it works fine. And also, one side benefit is that you don't have to have software fallbacks. I mean, the software is the fallback. It's its own fallback. You don't have to try this in hardware, and if it succeeded, great. Otherwise, do something in software. Production readiness. I know a lot of people have been burned by research code, and if you don't want to be burned, don't use it yet. This is kind of my scale of, the thing is, you see, you know, if you've got, when I started working my way through college, I had 2 users, right? And if I kept those 2 users happy, didn't matter what bugs I had elsewhere, that was fine. Later on in the 90s, I had like 6,000 installations. And that seemed really impressive at the time. I was impressed with myself and my employer with all that. But you know, if you only got 6,000 installations, Murphy's actually kind of a nice guy. You know, everything that can happen will, eventually. Maybe in geologic time. And you know, you get away with all sorts of stuff, and it just won't ever happen. Right now, with Linux kernel RCU, I'm well above 1 billion instances. There's supposed to be like 1.4 billion Android smartphones alone, right? And when you got a few billion users, Murphy can be a real jerk. I mean, everything can happen well, and it can happen really, really fast. All right, well, this stuff is not ready for that kind of environment. I'll give you that tell you that right now. The old stuff that required things, I got up to kind of the R&D prototype stage. This thing in June was probably at like limping. I think I got it to benchmark special at this point. So if you really want to use it in production, I would suggest a validation effort. And let me know, you know, I might be willing to help if you tell me about it. Thing is that the 1 billion is actually kind of not much, because Internet of Things is coming along, and we're going to get to 1 trillion pretty fast. And I don't know how to do that. Okay, I can actually make a test plan for Linux kernel RCU that'll do 1 billion users, and I can do that in about 18 hours of test time on a large machine. All right, I've learned a lot of dirty tricks over the last 25 years. All right. But 1 trillion's like 3 orders of magnitude more than that, and I don't know how to do that with testing. Fortunately, there are some people getting interested in formal verification, and I've heard rumors that there's 3 different groups that claim to have formally verified some part of Linux kernel RCU. Now, I take that with a grain of salt because they haven't reported any bugs. I know there's bugs in there, and they didn't find them. All right, so, but still, it's actually something that's kind of encouraging. These things might actually, after they've been telling me for decades, this stuff's great, you should use it, and you're going, that doesn't do anything for me. They may actually be getting to a point where it's actually useful in real life. Anyway, these are some antecedents of it, some things that have been done before, standing on the shoulders of giants and all that. And onto the summary here. We can actually do complex updates. We can do it to unmodified RCU protected structures. All we need is the ability to add, remove, and free the elements in the structure. The structure itself doesn't need to know anything about the atomicity or the complex updates. And you can use any synchronization mechanism you want in these things, and you can use any memory allocator you want, although you better use a pretty good one because it really hammers the memory allocator hard. You can automate the backout processing. And back when I was here last time, you had to do that by hand, and that was a real pain getting it right. So it's kind of nice having it automated. It just builds lists of the things it needs to clean up and needs to fix up. High update rate is a really good diagnostic tool. And the read mostly workload is considered to continue to work well. And I think that's mostly where people will be at. There's a lot more read mostly stuff than there used to be. And the same applies to the kaleidoscopic updates. And so it looks like there's a lot of opportunity for collaboration and innovation, although I'd feel better about it if I actually had some people using it. But you know, can't have everything, right? These are for the people that might want to dig deeper. And that's sponsored by Ebby and Legal. And again, as always, you've seen this many times, some of you. If you remember only one thing from this presentation, use the right tool for the job. You know, if my stuff's the right tool, great, use it. I'm proud of it. But you know, if my stuff's not the right tool, use something else. Anyway, we got a few minutes left for questions if people have any. Yeah.
So I'm not sure if I follow how exactly the readers are protected from seeing the analytic places, right? In particular,
Sure.
let's say I have a reader, navigates the first structure, finds the element.
Let me see if I can do this without crashing my display thing here.
Then I flip the bit, and then the reader still exists and navigates the second structure.
Okay, so like this, for example. So for what he's asking is, you know, how are the readers really protected? I mean, you've got all these updaters doing stuff. Why are the readers protected? So there's a couple things. One is that when the readers are going through and looking up the state, they're using an acquire load. Okay? And what that means is what you could have if you didn't have an acquire load is that both readers could go down that side. Now, the compiler could split them. Let me try to say that again. Let me try this over. If you didn't have an acquire load, the compiler could say, oh, we got two things that have nothing to do with each other, I'll just interleave them. I'll generate the code for them step by step in between, and you know, who knows what happens in what order, right? And it could, in fact, when you thought it was looking up the hash table first, it could look up the skip list first, because you don't have anything telling it not to. So you have to have an acquire read when it pulls out the indicator, the thing that points to this kaleidoscope structure. So that means the reads are going to pull them out in order. All right? So what happens, a bad thing, would be is if a reader came through and looked up in, we'll go to the next state here to see this. The reader could go through into the skip list, and it could look up element 1 and find it. All right? It would be really bad if it then went to the hash table, looked up element 1 and found it afterwards. That would not be atomic. But that can't happen because the two reads from the state variable are acquires, therefore they will be ordered. The compiler is not allowed to move them, the CPU is not allowed to move them. Okay? So that means that it looked up the skip list first and then the hash table. And then it went down here. It has to see the early value and then the late value. It can't go backwards because this relaxed load is not on to the same variable, plus the reads are forced in order. And so it can't see them out of order as a result. So the fact that relaxed loads are required to the same variable, are required to do atomicity, and the fact that we're doing acquires to get the address to load should do it. And if we wanted to be more careful, which I think you would, if we ever get it fixed, use a memory or consume to go through the pointer. As it is right now, I use volatile as we do in the Linux kernel because memory or consume is broken, although I think I'm getting closer. So that's a good question. Did that help? It's, yeah, okay. Other questions? Yeah.
So as you were describing, you were encoding some state in the lower bits of pointers.
Yes.
Does it mean that you have to use your own implementation of the linked list and hash table, or kernel ones, which comes with the Linux already knows how to
Well, see,
ignore these bits?
okay, so the question was, I'm using these bits in the lower bits of the pointers. How can I use the standard algorithms which don't expect those and have it work? That's a good question. Well, the trick is that the skip list is up there. I just look it up. There's no bits in anything until it gets to the element, and it hands me back this thing here. I got an element, and then the next level says, okay, great, that element's inside this thing, so get me the full structure. There's a pointer. Pick it up. Okay, and that's the thing that has the bits in it. So the thing that has the bits in the pointer isn't exposed to the skip list or the hash table. It's a wrapper around it. In C++ terms, you'd probably take, so you have an element in a skip list, you have an element in a hash table, you would inherit this other structure from those. So you have a skip list, and then you have the pointer as not in the base class, but in the, derived class? Derived class. It's, yeah. C, yeah. I'll let you talk Linus Torvalds into taking C++ into the kernel. Anyway, so what happens then is that if you think of it that way, the R superprotected algorithm is the base class, and the pointer with the bits is in the derived class.
So there is a getter and setter, is it what you're saying? And your getter setter actually?
It's just that the algorithm for the base class doesn't ever look at the stuff that's in the derived class. Because, I mean, it can't, because it's the base class. Okay, the way I do it in C is I have a field that's the thing that the skip list expects, and I have some other fields after it. The skip list is only going to mess with this structure here. There are no bits on the bottoms of pointers.
That's what you're messing with. Like, let's say it's linked list, it would be every we'll change the bits there. No?
Oh, here I went past it. Let's see if I can. Okay, so this thing, the struct skip list, is the thing the skip list algorithm looks at. It's just standard, normal pointers, no bits.
That's not where you put your bits.
That's right. This thing is just a pointer to the header of the skip list so I can find it. And then the bits are in this existence head guy. Okay, and so the skip list doesn't have to know about that. But yeah, I should have made that distinction clear to begin with. Okay, I think we're out of time. Thank you very much for your time and attention. It's been fun. It's not useful on Graham. Hope you got fun with this as well.